home. My name's Paige. I'm at the library, and I'm joined today by Dr. Daniele McKay. She is going to be talking to us about how to prepare for disasters, because we do live in volcano and earthquake country, and we need to be prepared for this kind of thing. All right, so before I begin, we are doing this program hybrid. So what that means is that there are people at home, and people here in the room. So people at home, if you have any questions, please put those into the Q&A or the chat. We'll be monitoring both throughout the program. So if you need anything, just go ahead and throw it out there and I will answer. And then don't forget that we're kind of in the middle of May here, and our new event guide for June, July is coming out quickly. So take a look at that online, get a sneak peek, but don't forget about all the wonderful programs that we have going on through the rest of May. This month we're exploring wonder. So for instance, I wonder how I would prepare for a disaster should it occur. That's what we're doing today. We also have some great programs like how to cook with herbs and spices, and what we did yesterday, my presenter was talking about how we're going to thrive in a hotter, drier climate. The world is heating up in Deschutes County, you know that for sure. So check out that program. If you missed it last night, you can check out our recording at deschuteslibrary.org. We have all sorts of great fun programs, so check them out. Okay, our presenter today is Dr. Daniele McKay. She is an adjunct instructor in the Department of Earth Sciences at the University of Oregon. She lives in Bend, Oregon, and teaches online geology courses throughout the academic year and field courses in Central Oregon during the summer. Her research background is in physical volcanology with a focus on recent mafic eruptions in Central Oregon Cascades. She's also interested in how societies prepare for and respond to natural disasters, especially volcanic eruptions and earthquakes. She has worked with Deschutes County, the Oregon Office of Emergency Management, Oregon Partnership for Disaster Resilience, and the Red Cross on natural hazard preparedness and mitigation in Central Oregon. So thank you, Dr. Daniele, for being here today to talk to us.
Thank you, Paige. All right, so thanks everyone for joining us here in the room and out there in your homes. So before I get started on this talk today, I just wanted to do a very brief plug for the Central Oregon Geoscience Society. If you're interested in any geology related topics, which you're at least partially interested if you're here today, this is a nonprofit organization based in Central Oregon, and we bring speakers once a month. We're hoping to go back to in-person soon, but even when we do go back to in-person, we will still offer talks through Zoom. We also organize field trips, and we do a lot of support of education by giving grants to students who are doing any sort of earth science related project in Central Oregon, and supporting K through 12 education throughout Central Oregon. So check out that website. This is just a screenshot of the homepage. Check out that website if you're interested in more information about geology in Oregon and Central Oregon specifically. All right, so the outline for today, this really is more of a geology talk, but we will wrap it up by kind of coming back to how can we prepare for some of the events that we'll talk about today. So first we'll look at why do volcanoes and earthquakes occur in the Pacific Northwest? And what could future volcanic activity and earthquakes look like here in Central Oregon specifically? And how should we prepare? We'll end up by how we could prepare for these events. So just to start things off, this is an image that shows the plates, the major plates on the surface of the planet. So if you think about any geology classes that you might have taken or things you know about the Earth, the basic construction of the Earth is the core in the center, the mantle, and the crust. And the crust is brittle, and it's so it's these brittle plates, and the Earth, as we know, is round, which means that those brittle crustal plates must be broken into pieces in order to fit on this round globe. So those plates are in constant movement, and here in the image, the yellow lines outline plate boundaries. So that's the Pacific Plate, one of the largest plates on the planet. Also notice there's this very small little plate here right in our neck of the woods. This is the Juan de Fuca Plate, kind of sandwiched between the large North American plate and the large Pacific Plate. So we're going to kind of zoom in on that Juan de Fuca Plate in a minute. But the movements of plates explain the occurrence of volcanoes and earthquakes worldwide. These plates are in constant motion, and the ways that they interact with each other really explains where we have earthquakes and volcanoes. So let's zoom in to the Pacific Northwest and look at that little Juan de Fuca Plate. a little more closely. So there it is, this line here, everything to the left of that line is the Pacific plate, and everything to the right of that line is the Juan de Fuca plate. And the Juan de Fuca plate is not a very big plate at all. It ends right here, which means everything to the left of this line is the Juan de Fuca plate. Everything to the right of this line is the North American plate. And these little triangles or teeth indicate that the Juan de Fuca plate is actually subducting beneath the North American plate. And I'll get to another slide that shows that in a minute. And that subduction zone, so that line is what we call the subduction zone. And here in this part of the world, we've given it a name. It's the Cascadia subduction zone. And it is a 600-mile long fault, essentially. This is the fault. When you hear about big earthquakes in the Pacific Northwest, it would be along this entire zone, or maybe along just a portion of it. But essentially, that is a 600-mile long fault zone that runs from southern British Columbia to northern California. So in this next image, this is a map image as if we're looking down. Now we're going to go to an image that's a cross section. So it's like if you took a big giant knife and you could cut kind of through the crust and expose what's going on at depth, east-west, kind of in the range of Mount Hood and Portland. So there's the subduction zone. That's that map symbol that shows that that Juan de Fuca plate here is subducting beneath the North American plate. So not only does this create a 600-mile long fault zone, this also creates a linear range of volcanoes that is parallel to the subduction zone. And the reason for that is as that plate gets deeper into the mantle, and in these images of the Earth, the interior of the Earth, the mantle is almost always drawn in these red and orange colors that kind of make you think that it's molten. It is not. It is a completely solid material. It's not a brittle material. It's a soft, sort of malleable, squishy material, but it is solid. So there is no magma or very little magma in the mantle. In order to get magma from the mantle, something has to happen. And in a subduction zone, what happens is the rocks that are coming in from this subducting plate have hydrogen and oxygen incorporated in the minerals of the rock. So if we could somehow drill down and collect a sample of the rock from down here, we can't. We don't have the technology to drill down that far. Believe me, geologists would love to. But if we could, and we could grab a sample of that rock, or if we just go here, we do have the technology to get down to the ocean floor. If we grabbed a sample of the rock there, we crack it open, water isn't going to pour out of that rock. The hydrogen and the oxygen are incorporated in the mineral structures of the rock. And those minerals formed at the surface of the Earth where this rock cooled as a volcanic lava flow. Those minerals are perfectly happy at temperatures and pressures that you find at the surface of the planet. When you shove them down into a subduction zone, they're not happy anymore. Pressure is incredibly high, temperature is high. Those minerals change from one type of mineral to a new type of mineral. So they basically undergo chemical reactions. Water is driven from those minerals. It's not liquid water like what we would recognize here on the surface of the planet. It is hydrogen and oxygen though. It's sort of this supercritical fluid because the pressure is so high and the temperature is so high. So the hydrogen and oxygen actually changes the chemical composition of the mantle, and that causes the mantle to melt, and that molten material rises up and feeds volcanoes. And the reason that melting occurs is when the chemical composition of the mantle changes by the addition of hydrogen and oxygen, it has a different melting temperature. So an analogy for that is on a cold day, if you have ice on sidewalks, you want to get rid of that ice, you sprinkle salt out on the ice. You didn't change the pressure, you didn't change the temperature, you changed the chemical composition of the ice. You did have water, frozen water. Now you have frozen water plus salt, and that has a different melting temperature. So same thing here. You have mantle material plus hydrogen and oxygen. It melts, it generates magma, and the magma rises up and feeds volcanoes. Now we're looking at a two-dimensional image that is conveying a three-dimensional process. So this subducting slab is not just coming in beneath Portland and Mount Hood. It's extending into the screen all the way up to southern British Columbia, and it's extending out of the screen towards us all the way down to northern California. So it's a three-dimensional slab of material. And everywhere along that slab, magma is produced. And so we get this linear range of cascade volcanoes parallel to the subduction zone. So now you can kind of picture what's going on literally beneath our feet as that magma is generated. Also notice, so in this image, The little black dots are actual volcanoes. So MH is Mount Hood, MJ is Mount Jefferson, TS is Three Sisters. So the actual volcanoes that we think of for the Cascades are labeled, but the red indicates all volcanic rocks that were created by these volcanoes. And notice that Central Oregon is really the most active section of the Cascades. There's more volcanic rock that has been produced there by these volcanoes than really anywhere else in the Cascades. So we definitely live in volcano country. And these are definitely active volcanoes because this process of subduction that's generating the magma is still occurring. So every day when we're out and about in Central Oregon, we're looking at volcanoes. I like to say if you see any topography in Central Oregon, it is almost always either a volcano or a fault line. There are some exceptions to that, but in many cases, they're volcanoes. So here, of course, is the Three Sisters and Broken Top. And this is kind of what we think of when we think of the volcanoes in Central Oregon, South Sister, Middle Sister, North Sister. But I like this picture because it's taken from the slopes of Mount Bachelor, which is another volcano. And you can just see poking up Egan Cone, which if you like to ski at Mount Bachelor and you like to ski the cone at Mount Bachelor, that's the cone. So this is a little cinder cone. It's a little volcano on the side of a volcano, Mount Bachelor. And we're standing here on the side of the volcano looking out at the big volcanoes that we all love and recognize, but all these little bumps in between, a lot of those are also volcanoes. So they're really everywhere in Central Oregon. This is Newberry Volcano. This is the summit of Newberry Volcano, which is a caldera, much like Crater Lake. It's a depressed feature that was created by a huge volcanic eruption. And this is Paulina Peak. So if you stood up on Paulina Peak and looked down at Paulina Lake and East Lake, and there's very recent lava flows in this image. You can see these very recent lava flows, little cones. So again, a very active volcanic area. And Newberry Volcano, it's hard to capture the scope and scale, the size of Newberry Volcano. This is an image that was taken from Bend looking south, and Newberry Volcano occupies the entire skyline when you're in Bend looking south towards Sun River and La Pine. Newberry Volcano is this very large shield volcano, and actually the entire volcano isn't even captured in this image. It extends a little out of the image here and out of the image here, and it's got all these cinder cones, hundreds of little cinder cones or smaller volcanoes dotting its slopes. So Newberry Volcano, even though it's not tall and pointy like these guys, doesn't stick up high in elevation, it is by far the largest volcano in the Cascades when we think of the volume of Newberry Volcano. It's also one of the most recently active volcanoes in the Cascades. And there's clear indications that it could erupt again. There are very recent lava flows, so it has erupted recently, which means it could erupt again. There are hot springs kind of in this area over here along the lakes. There's some gas emissions and fumaroles over here. So there's lots of activity that shows that there's still magma beneath Newberry Volcano and that it could still erupt again. All right, and then this is a picture of Lava Butte between Bend and Sun River, and it just shows that these are really very young volcanoes. This is a cinder cone. The eruption created the cone itself, and then lava flows emerged from the base, and these very extensive lava flows made their way west towards the Deschutes River and actually dammed the river. But I put this in just as a reminder that there's not a lot growing on these lava flows, which is a really good indication that these are very young volcanoes and a good indication that activity could start again here in Central Oregon. So this is a topography map. Here's Bend, Redmond, Sisters, highways are shown on the map, La Pine, Sun River is right around here. And then Newberry Volcano is labeled there on the map. So that's just the summit with the two lakes of Newberry, but the footprint of Newberry is very large, kind of covers this whole area of the map. And then Mount Bachelor and the Three Sisters. And I'm using this topographic image because if you really look, you can see all these little bumps all over them. They look like pimples kind of scattered all over the map. Those are all cinder cones. So we really do have, not only do we have the big volcanoes that I just looked at, but we have literally hundreds of cinder cones scattered across the landscape in Central Oregon. So not only could an eruption occur at Newberry Volcano, or within the Cascade Range itself. But cinder cones could occur anywhere. There's actually a cinder cone right in the middle of Bend, Pilot View. So it's a really good indication that we could have volcanic activity anywhere throughout Central Oregon, not just up high in the mountains somewhere. And then this is just another map. Bend, Lapine are labeled on the map. Highways aren't on the map. Here's Sisters. Here's the Deschutes River. No highways, but all of these dots, here's kind of the main crest of the Cascades. Mount Bachelor is here, Broken Top, North Sister, Middle Sister, South Sister, Mount Washington, Three Finger Jack. And all of those blue and red dots on the map are all volcanic vents. So we kind of think of individual volcanoes. There's Mount Bachelor. Okay, got it. That's a volcano. There's South Sister. That's a volcano. But it's not just those ones that we see in the skyline. It's hundreds of individual volcanic vents that have each produced lava flows or ash or something, even though they might not have built up a big volcanic edifice. So they really are everywhere. And notice that these black lines here are also kind of everywhere throughout the right side of the map. These are all faults. So there's this whole string of faults that goes through Bend and through Sisters. So we'll talk about those in a minute. Okay, so let's just do a little background on how we measure volcanic eruptions. This is called the Volcanic Explosivity Index, or VEI scale. And the scale is based on the volume of ash that was erupted from a volcano, the height of the eruption column, so how high into the atmosphere that ash was blasted up, and then maybe carried by the wind or deposited in some other way, and then how long the eruption lasts. This is really the key here, is the volume of ash erupted, but there are these other factors that play into this scale. So these spheres here represent numbers. The VEI, or Volcano Explosivity Index, goes from 0 to 8. 8 is actually not shown on this. I'll show some examples of 8s in a minute. And then the spheres represent that volume of material that was erupted as ash. So you can see this big one is Tambora. This is an eruption that occurred in 1815, very large eruption. Had some global climatic impacts. It caused some global cooling for a few years after the eruption. This is Pinatubo, which erupted in 1991. This is also more or less the same size as the eruption of Mount Mazama that occurred about 7,000 years ago to create Crater Lake. This is the 1980 eruption of Mount St. Helens. Many of you living in the Pacific Northwest probably remember that eruption. And then you get into some smaller eruptions. These ones are all examples from California, but there are many eruptions like this, throughout the world. So, and then, no, this is Tambora. Yellowstone caldera is not shown on here, and I will show an example of Yellowstone and some other volcanoes in just a minute. But first, I just kind of want to mention that the larger eruptions occur less often, and the smaller eruptions occur more often. Worldwide, that's the case. So that's good news. More volcanic activity is in this end of the scale. It's less often that we have this end of the scale, but this end of the scale, it causes much more damage. All right, so let's go back to this Yellowstone caldera, not depicted in this image. So I'm going to go to this image, and the scale of things like Yellowstone and what would be a VEI 8, remember we're rolling on to 7 on this scale. The scale of a VEI 8 is orders of magnitude bigger. So here is Tambora, the largest one that we looked at just a minute ago. And this is actually Nova Erupta, which erupted in 1912, but it's more or less the same size as Tambora. No, sorry, that was not my reference point. I'm sorry. There isn't anything that exactly represents Tambora here on this scale, but there is Pinatubo. There's Pinatubo here, and here's Pinatubo here. So I put these scales at more or less the same size. You can see, okay, Pinatubo is a pretty big volcanic eruption. It's between a VEI 5 and 6. There it is on this scale. Mount St. Helens is here. There it is on this scale. We don't have anything totally equivalent to Tambora, but it would be something around like this, a little bit bigger than Nova Erupta. And then we get into these VEI 8s, which are called supervolcanoes because they're so huge. And that's what that Yellowstone caldera, the one that they called out here in this first image, that's this eruption here. Very, very large, but not the largest eruption that we know of on Earth. The largest eruption that we know of on Earth was Toba, which erupted 74,000 years ago. That's also the most recent example of a supervolcano eruption. So 74,000 years ago, people were around, but they weren't keeping any written records. And we don't have, that's so long ago that we have no oral histories or anything remaining from those people who were around to witness that eruption. So we don't actually know what it would be like to be on Earth during and after a supervolcano eruption. We can make some really good, predictions based on what we've seen in the geologic record. But these would definitely be something that, if the eruption of Pinatubo had some impacts on climate and the eruption of Tambora had some impacts on climate for months to years, these would have impacts on global climate for maybe decades to centuries. So notice there's a little dashed line right here. And that dashed line is the Crooked River caldera, which is right here in Central Oregon. So when you go out and visit Smith Rock, you're looking at volcanic products of Central Oregon's own supervolcano. This erupted about 29.5 million years ago, so it is very extinct. We don't have to worry about a supervolcano eruption occurring in Central Oregon. So I'm just going to go back and look at some of the types of eruptions that could occur in Central Oregon. So we can take supervolcanoes or VEI8s off the list. But we could have something in this range here, like Mount St. Helens or Pinatubo. And here's a picture of the 1980 eruption of Mount St. Helens. This was in Washington. But past activity in Central Oregon has been similar to what we saw in 1980 at Mount St. Helens, producing very thick deposits of ash and pumice and this type of rock called welded tuff, which we just saw at Smith Rock. So this is a picture in the Tumalo State Park area that shows just how thick some of those ash and pumice deposits are from past eruptions in Central Oregon that were similar to the 1980 eruption of Mount St. Helens, or maybe even a little larger. So these eruptions covered what is now the bend area in many feet of ash and pumice, also more dense rock called welded tuff. This is right along the river in kind of the old mill area at Riverbend Park in Bend. And this is thick deposits of rock that was produced by a highly explosive eruption in the past. But the majority of eruptions in the past in Central Oregon have been less explosive. So remember that scale. The big, dangerous, really dangerous eruptions occur less often. The smaller eruptions occur more often. So this is actually more like if we have renewed volcanic activity here in Central Oregon, this is more like what it might look like. So less explosive eruptions have produced some volcanic ash, but also cinder cones and very extensive lava flows. So this is an image taken from Mackenzie Pass, and it's looking at North Sister and Middle Sister, and that's what our eyes are drawn to, are these big, tall, beautiful, snow-covered volcanoes. But there's just this sea of lava in the foreground. And that's really what most activity in Central Oregon has looked like. It has produced very extensive lava flows and cinder cones. It's kind of hard to see because they're dwarfed by North Sister, but that's a little cinder cone called Collier Cone. That's another one called Yapoa Crater. So these cinder cones really are everywhere. And that's what's producing the lava flows. The lava flows come out of the base of these cinder cones, like Lava Butte. And again, just as a reminder, they're everywhere. These little cinder cones are just scattered throughout the landscape in Central Oregon. And another thing I'd like to point out in this map is there's very high rough topography in the volcanoes themselves. Newberry has high topography, but most of the topography throughout like Lapine and Sun River and Bend and up to Redmond, most of that topography is relatively flat. And the reason for that is it has been covered with lava flow after lava flow after lava flow. So it's essentially been paved over with lava flows. And since these things are molten when they're flowing and then they cool and solidify, they leave more or less flat topography. Now, if you had to walk across them, they would be quite difficult to cross, but the topography is relatively flat on a large scale. So this map, you can tell a lot by this map in terms of how, what we might expect in future volcanic activity just by seeing the number of cinder cones scattered throughout the map and the flat topography, which really indicates we've had a lot of lava flows here. So what could future activity look like? Here's a picture of a lava flow from the 2018 eruption of Kilauea in Hawaii. You might remember this eruption. It came through a subdivision and destroyed many homes. We'll take a look at that in a minute. This is part of eruptive activity that has occurred since 1983 at Kilauea. So this represents decades of on again, off again volcanic activity. The lava flows weren't flowing constantly throughout that time, but they periodically start up and stop again. And so that's something we could see in Central Oregon, that we have a volcanic eruption, but it kind of lasts for a couple weeks, stops, and then 2 years later it picks up again. And that kind of activity continues for decades. So that's a possibility here in Central Oregon. And that type of activity can produce fire fountains. We'll look at some pictures of fire fountains in a minute. Extensive lava flows, and you can see the lava flows have no regard for roads or houses or infrastructure. And volcanic gases can also be a problem with these types of eruptions. Also, especially here in Central Oregon, in Hawaii, these lava flows can start fires. And the fires are usually pretty easy to put out, but here in Central Oregon, you can imagine if a lava flow like this happens in summer or fall, how many fires would be started along the perimeter of it, and then just how quickly those would spread, and how difficult it would be to kind of deal with an active volcanic eruption at the same time as multiple fires. So something to kind of think about. Again, the lava flows, there's the lava flow kind of invading on this house. The house bursts into flames first and then gets covered with the lava flow. There were 2,000 people evacuated just during the 2018 eruption. 2,000 people evacuated, over 600 homes were destroyed, and that caused about 800 million in damages. Notice that the injuries, relatively low, no deaths, and relatively low injuries. So this type of volcanic activity in general, especially in developed countries like the United States, has a low death and injury impact and a very high economic impact. All right, so other examples, recent examples from around the world of what we could expect to see here in Central Oregon. So this is the 2021 Cumbre Vieja eruption in La Palma. La Palma is an island in the Canary Islands. It's part of Spain. And this happened just a few months ago. And the eruption occurred, I was teaching a hazards class last fall, and the eruption started in September, right around when the class started. And it continued throughout the entire term to December, when the class ended. The whole time we were talking about, natural hazards, this eruption was occurring in La Palma, and people were dealing with it in cities in La Palma. So it lasted for 3 months. There's a picture of a fire fountain. So that's volcanic activity blasted up and kind of cools in the air and falls back down. That's what builds a cinder cone. This is the process of a cinder cone being built in a neighborhood. So this is not off in the mountains somewhere. This is in your backyard potentially, and that's the same scenario that we have here in Central Oregon. Volcanic gases were a real problem in this eruption because it's an island. These lava flows ended up at the ocean, and when they entered the ocean, they started generating things like sulfuric acid as a gas, and so that can be really dangerous. That's not something we have to worry about as much here in Central Oregon. But the lava flows themselves do give off some gases. So it's definitely a hazard to consider. 7,000 people were evacuated during this event. Part of that was sometimes because of the gas clouds near the ocean. Over 3,000 buildings were destroyed. And again, about $876 million in damages. One death, although that hasn't been confirmed that it was actually related to the eruption. So again, very low death and injury toll, very high economic damage from these types of eruptions. And I just wanted to put this picture in because even though most of what this type of activity produces is lava flows, there's still very extensive ash deposits. This is a house, and you can see that it's pretty much buried in ash. So even though these eruptions aren't producing ash on the scale of the supervolcanoes and the big VEI like 6s or 7s, they're still producing enough ash that you'd have to deal with a lot of ash if it's happening in your backyard. And then finally, another eruption that was similar to what we could see here in Central Oregon. This is a 2010 Eyjafjallajökull eruption in Iceland. You might remember this eruption because it was in the news quite a bit because it produced quite a bit of ash on the scale of these sort of smaller eruptions. Produced quite a bit of ash, and that ash impacted air travel in Europe. So it was in the news quite a bit because it shut down air travel. So this eruption lasted for about 3 months, Again, produce fire fountains, lava flows, volcanic gases. Because I'm putting this picture in because this is, unlike Hawaii and the Canary Islands, this is a little more similar to the Cascades in that these are snow-covered volcanoes. So in the winter, we would have this could be Central Oregon instead of Iceland. It's like kind of a rural area, a lot of farmland and snow-covered volcanoes. And when volcanoes erupt under snow, they can produce flooding. So there was quite a bit of flooding associated with this volcanic eruption that you didn't see in Iceland or the Canary Islands. But that's something we could see here in Central Oregon for sure. And then produce this volcanic ash, and the ash shut down airports throughout Western Europe. All those red dots represent major airports that were shut down intermittently. All flights were canceled. In Iceland itself, 500 people were evacuated. It was a rural area, so not a huge number of evacuations, but more than 100,000 flights were canceled and 1.7 billion in damages because of the disruption in global transportation. This is 2010, obviously pre-COVID. Now we're like, global disruption in transportation, we're used to that. But this was one of the first times that something like that happened that had such global impact. So very large damages there. And then back in Iceland, the ash really can be an issue. And again, I'm using Iceland because it has some similarities to Central Oregon, that it's a rural area. These guys are trying to gather up their livestock. Notice that they're all wearing masks. So one take home of this message is, don't get rid of your masks yet, because you want to have those in your emergency kits. So they're rounding up livestock because this ash is very dangerous to livestock if they ingest it. They're also getting ash off their roofs because, unlike snow, ash is much more dense and it doesn't take that much to collapse roofs. So they all have to get up there and start shoveling ash off of their roofs. And driving in ash can be very, very difficult. You can imagine the visibility of this. It also can clog air filters, abrade windshields. And now that almost all cars are entirely computer run, it can mess with electric systems. So in some cases, your car might not even start because of the ash messing up with the electrical system of your car. So ash is an ongoing problem even after the eruption is over. Okay, so back to doing with time. So this was a volcanoes and earthquake talk. So we're going to go back to the earthquake part and what earthquakes might look like here in Central Oregon. So remember, it all has to do with the subduction of the Juan de Fuca plate under the North American plate. And I'm going to just do a little, we talked about how volcanic eruptions are measured. Now we're going to talk about how earthquakes are measured. So they're measured using the moment magnitude scale. You will often see a report, maybe in the news, of an earthquake, and it's given a number and it says the Richter scale, and that's not correct. We use the moment magnitude scale. The two scales are based on the same principles, but the Richter scale just has less applicability to all earthquakes worldwide, and the moment magnitude scale really can be used to measure all earthquakes. So this is the scale we use. It compares the amplitude of the waves measured on a seismogram. So this is a seismogram. This represents no earthquake. This represents the very first earthquake wave. So the machine itself is recording earthquake waves. And then this represents the larger earthquake waves that would cause damage. The amplitude is the height above or below what represents kind of zero, no shaking. The amplitude is how high that line is above the what would be zero line. So each unit on the moment magnitude scale is 10 times larger than the unit before. So a magnitude 2 earthquake is 10 times larger than a magnitude 1, but that's all based on how high up these lines go, the amplitude. So that's super useful for seismologists who study earthquakes, not as useful for the general public. Like, why do you care how high this line is off there? You want to know, what is the earthquake going to do to you? What is it going to feel like? So, and the other thing that's kind of maybe not as intuitive about that is that I think we're all aware that each unit is 10 times larger than the unit before. A magnitude 2 is 10 times larger than a magnitude 10, but that's measuring the amplitude. The amount of energy released between each unit is 32 times more than the unit before. So a magnitude 2 is 32 times more energy than a magnitude 1. So I have an animation here that kind of puts in, kind of like the volcanic eruptions, it puts the scale of this stuff into spheres. So let me just get this started. All right, so we're going to start with a magnitude 5.8, and then this represents a 6.7, 6.9, and a magnitude 7. That's the 2010 eruption in Haiti. So as we get bigger and bigger spheres, we're getting larger and larger magnitude earthquakes. So we're still at we haven't gone beyond a 7 yet. You can see kind of the scale. Remember, this is representing the amount of energy, which we're going to feel as shaking. So now we've gone from a magnitude 7 to, wait for it, a 7.8. We haven't even got to the next number, which is an 8. Now 7.9, 8. We're finally at a magnitude 8. And then we're going to have a ways to go before we get to the sphere that represents the amount of energy that's released in a magnitude 9. And now look at the perspective of what we started with. I mean, they look tiny, but these were very damaging earthquakes. 7 is nothing to scoff at. All right, we're almost there. So magnitude 9, this is the 2011 earthquake in Japan. Magnitude 9.1 is the 2004 Indonesian earthquake. 9.2 is the 1964 earthquake in Alaska. And the largest earthquake we've ever measured was a 9.5 in 1960 in Chile. I guess I didn't really need quite so much dramatic music with that. All right. So I think that really helps put it into perspective, how much energy is released. And here in the Pacific Northwest, when we talk about large earthquakes on the Cascadia subduction zone, this is what we're talking about. A magnitude 9, so here, a magnitude 9 or larger, or perhaps a magnitude 8 or larger. And these are the largest earthquakes on Earth. The big earthquakes that occur in California are all in the magnitude 7 to 7.8 range, maybe. So if you think of being in a relatively, like a pretty scary large earthquake in California, or the big one that's expected in California, that's in this range. This is what we're expecting here in the Pacific Northwest. All right, so let's look at, one more way, real quick, of measuring earthquakes. That was the moment magnitude scale. This is called the Mercalli intensity scale, and this is actually much more intuitive for you and I, wondering what is it going to do to our house, to the landscape where we live. It's a scale that uses a color rating, which is very intuitive to us. It's kind of what we're used to for fire and other hazard scales. And it rates the effects of earthquakes on the Earth's surface based on how you feel an earthquake, how much shaking, and the damage caused to man-made structures. So notice that the magnitude scale, a magnitude 2 earthquake, doesn't correspond directly to the moment, to the Mercalli intensity scale. They aren't equal. It's 2 totally different scales. So if we're talking about a magnitude 8 or 9 earthquake along the Cascadia subduction zone, that doesn't mean that it's going to cause extreme damage everywhere. It really depends on where you are. But you'll see this scale again. This is really helpful for just kind of defining the amount of shaking that is going to occur. And I know you can't read all of this information, but if you just Google Mercalli intensity scale, you'll get the same image or something like it, and you can read all of that info. All right, so here in the Pacific Northwest, we have 4 types of earthquakes. And here again is the Juan de Fuca plate. Everything to the left of that line is the Pacific plate. Everything to the right of that line is the Juan de Fuca plate. The Juan de Fuca plate is subducting under North America. There's the volcanoes that are produced. And at that place where the plate is subducting, the 2 plates are touching and they're locked. That's what those pink lines are showing you, is that they're locked. And that's bad news in terms of earthquakes. So now I'm going to just kind of drop down this area so that we can see a cross section of the Juan de Fuca plate subducting beneath the North American plate. There's the magma generated, it creates volcanoes. And this shows all of the types of earthquakes that we have here in the Pacific Northwest. One is subduction zone earthquakes. Those are the ones that occur right there where the plates are locked. That's what the rest of this talk will focus on, because that's what everyone really wants to know about is very large Cascadia subduction zone earthquakes, but we also can have deep intraplate earthquakes. So those are earthquakes that occur in the Juan de Fuca plate itself as the plate is subducting. Subduction zone earthquakes can be magnitude 9 or larger. These earthquakes are smaller, magnitude 7, still nothing, you know, they're still relatively large earthquakes, but because they're deeper, they usually cause less damage. Volcanic earthquakes can be magnitude 5 or larger. Usually they're more in the range of magnitude 2. And that's earthquakes that are generated as magma is moving up towards the surface. And those earthquakes are actually great because they're almost always too small to cause any damage, but they give us warning that magma is moving towards the surface and we need to prepare for volcanic activity. So those earthquakes are actually really helpful. Crustal earthquakes are earthquakes that occur within the North American plate itself. And here's a map showing crustal faults, places where earthquakes could occur in Oregon. So yes, we have this Cascadia subduction zone off the coast of Oregon in the Pacific Northwest. And yes, we could have a very large Cascadia earthquake, but there are also faults running throughout the entire state and into central Oregon. And these faults they haven't been active for thousands or hundreds of thousands of years, but that doesn't mean that there could be new earthquakes on them. There could be. So we also have faults here, right here underneath us in central Oregon. Those would produce much smaller earthquakes. Remember, if we go to crustal faults, maybe magnitude 7, maybe smaller. We don't have a very good handle on how often they happen. They're smaller than the subduction zone earthquakes, but because they could occur directly underneath us, they could cause just as much damage. All right, so let's focus on the subduction zone earthquakes, since that's really the big one that everyone talks about, and there's lots of questions about what's going to happen when that happens. So this is just a timeline. We're here, and we've been able to construct a timeline going back actually about 10,000 years. This goes about 8,000 years ago, but we've been able to construct a geologic record of big subduction zone earthquakes that have occurred here in the Pacific Northwest along the Cascadia subduction zone. So every time you see a longer red line, that's an earthquake that was magnitude 9 or larger. And every time you see a smaller red line, that's an earthquake that's magnitude 8 or larger, still one of the largest earthquakes on Earth, right? So we have this whole history throughout the past 8,000 years of when these earthquakes have occurred. And if we do some statistics on that, there have been 19 magnitude 9 or greater earthquakes that occurred along the entire length of the Cascadia subduction zone. That averages out to about one earthquake every year. Now that's just statistics, it's just averages. Earthquakes don't follow averages, so that doesn't mean that they come every 500 years. It just means that's more or less the amount of time between them. During that same amount of time, there have been 22 magnitude 8 plus earthquakes, so between an 8 and a 9. And usually that's just the southern end of the subduction zone, kind of in southern Oregon and northern California that ruptures. And if we average that out, that equates to about one earthquake every 250 years. So that's why you hear these different years, like, oh, they occur every 300 years, they occur every 600 years. Well, what is it? It really kind of depends on which statistical analysis you're looking at. So together, if you kind of look at all of that and do some statistics on all this, the magnitude 8s, the magnitude 9s, 75% of all of these events have occurred within less than 300 years apart, or 310 years apart. So that means that most of these events, they have about 300 years between them. Again, the earthquakes don't know that. They're not going to follow these numbers, but that's why roughly we say they occur every 300 years. The last one occurred in the year 1700. So it has been 322 years since that last earthquake. Some people take that and interpret it as, oh, well, we're overdue. They're supposed to occur every 310 years, and it's been 322 years. So where's the earthquake? That's not how earthquakes work. It's not overdue. We don't know when it's going to happen, but we do know, based on geologic records, that it will happen again. So there's a 10 to 15% chance of a magnitude 9 earthquake occurring in the next 50 years, and a 37% chance of a magnitude 8 occurring in the next 50 years. So those are pretty high. Like if you saw those kinds of 37% chance of rain, you might bring a raincoat with you wherever you're going. 37% chance of an earthquake in the next 50 years is a good indication that we should do some things to prepare for that earthquake. All right, so what could this look like? This on the left is that Mercalli intensity scale, so the amount of shaking that we feel as people for the 2011 earthquake in Japan. And so the red indicates a lot of shaking, and then as you go towards yellows and greens and blues, it's less shaking. So that's the actual shaking map for the 2011 magnitude 9 earthquake in Japan. This is an estimated shaking map for a magnitude 9 Cascadia earthquake. So you can see there would be much more area that would have extreme shaking than there was in Japan. And this is only showing Oregon. This would also extend up into Washington and southern British Columbia and down into Northern California. So more of an area impacted for sure, but fewer population. The population in this part of Japan is very, very dense. That doesn't mean, I mean, we still have very dense populations here for our standards, but the coast in particular is not nearly as densely populated as it is in Japan. Shaking for a magnitude 9 or a magnitude 8 earthquake can last for 5 minutes. This is another difference between these earthquakes and earthquakes in California. The magnitude 7s, they usually last for maybe 30 seconds, maybe a minute. These big ones can last for up to 5 minutes. So that would feel, I don't know if any of you have ever been in an earthquake, but it probably felt like it lasted forever. And 5 minutes would really feel like forever. All right. So how are we looking here in Oregon? So most of our schools and many critical response buildings in Oregon were built before there were seismic codes. So here's a 1900, 1910, this goes all the way up to 2000. Right around 1990s when the first seismic building codes in Oregon were put in place, a little bit before that. And these scales here, or graphs here, are just showing that most of our K through 12 schools were built in the 1960s prior to any seismic code. So those schools are not expected to withstand an earthquake. Fire and police, again, most of them were built in the 60s and 70s prior to seismic codes. And then community colleges, more or less the same thing. So the overall take home here is just that many of our public buildings weren't built to seismic codes. So we have some work to do there. This is an analysis of schools and emergency buildings. It's the collapse potential. So if you see a red dot, it has 100% potential of collapsing during a magnitude 9 earthquake. Orange dot has more than a 10% chance. Green is moderate, more than a 1% chance, and low is less than a 1% chance of collapsing. So of course, there's lots of red dots in places through the Willamette Valley and along the coast where we think most of the damage from the earthquake will occur, but there's plenty of red dots in Central Oregon and all the way throughout the state, which means not only are these buildings susceptible to a Cascadia earthquake, but also to regional earthquakes along regional faults. So we have some work to do for our infrastructure. This is just, if you're curious, I wish this existed for the whole state, but if you're curious about looking at individual buildings, there is an app that you can do that for Portland. You can zoom in, you can enter an address and it'll zoom right into an area and it will show you the potential for collapse of that building. And it's all based on when it was built. I'll get to that in a minute. That's because of seismic codes. So you can see there's a lot of red in Portland, a lot of buildings that were built prior to seismic codes, and so a lot of potential damage there. Bridges on all major transportation routes in Western Oregon are vulnerable to damage. This is the bridge that crosses the Columbia River in Astoria, but there was an inventory of all bridges along 101 and I-5, and these, a bigger sphere represents total collapse. Smaller represents extensive damage, but not collapse. You still would want to drive across that bridge. Moderate damage, you still probably wouldn't want to drive across the bridge, and then slight damage. And you can see that there's just bridges all up and down the Coast Highway, I-5, and all of the roads that connect them. So bridges would be out throughout Western Oregon. The inventory didn't extend into Eastern Oregon. Unfortunately, it would be really nice to know how our bridges would fare, but we haven't got there yet. So the estimated time to partially repair I-5 after a magnitude 9 earthquake is 6 to 12 months, and 101 is just years. We don't know how long it would take to completely get that up and going. Earthquakes are also likely to trigger multiple landslides. So this is a map that shows Oregon. And all of those yellow dots are landslides that have occurred within, like we have historical records of those landslides. So only in the last few, 100 years have those landslides occurred. So lots and lots of landslides in the Coast Range, lots of landslides in the Cascades, and of course shaking, especially if the earthquake occurs in winter months when things are wet, could trigger lots of landslides cutting across access across the Cascades. So roads could be closed across the Cascades. And here's an example of a landslide. This was a magnitude 6.5 earthquake in Taiwan. And you can see it's going to take some time to get that road back up into any kind of operable state. And so this is what could happen to major east-west routes across the Cascades. Even if roads are functional, fuel will be in short supply because more than 90% of all of Oregon's refined petroleum products, so that's all the gas for our cars, all the gas for planes, any firefighting equipment, all liquid fuel comes through this hub on the Willamette River in Portland, and it's built on these loose river sediments, and it is not expected to withstand an earthquake at all. This whole area will suffer significant damage. Essentially, the fuel tanks will sink into the river sediments, spill into the river, so it will cause a huge ecological disaster because of the fuel spill, but also the state will have no fuel until we get it from some other source. So for you and I, that means when we go to the gas station, this is in, I think New Jersey, it was Hurricane Sandy. So New York or New Jersey, we wouldn't see that sign here in Oregon, but we would see something like this: no food, no gas, no something, I don't know what it is, but they don't have it, and no power. And so we would definitely not be able to get gas from gas stations for a while. All right, so this is just an estimate from the state of Oregon for restoring facility or infrastructure and critical services. So in the coast and the Willamette Valley, to get electricity back up and running would be in the range of, kind of 3 to 6 months. To get drinking water and sewer, these are super important, drinking water especially, 1 to 3 years for the coast and 1 month to a year in the valley. Top priority highways, partial restoration only for emergency services, 6 to 12 months in the valley. Police and fire stations for the coast is 3+ years. For the Willamette Valley is 2 to 4 months. And for Eastern Oregon did get some analysis for this, so this would be us. 3 days to a month, we really don't know for sure. It depends on how much damage those buildings suffer. Healthcare facilities, 3+ years for the coast, 18 months for the valley, and about a month for Eastern Oregon. So that means that the healthcare facilities that are up and running in Eastern Oregon are the healthcare facilities for the entire state, while everything else is restored. And we kind of have a taste for this now with COVID. Businesses can only tolerate 2 to 4 weeks of disruption of essential services. And we saw that, businesses have really been struggling with COVID, but the disruption caused by COVID is not nearly to the extent of what we're talking about here. So this is, again, high economic damage. And, hearing all of this, you might think, what are we thinking? Why have we built this way? If we live in a place where earthquakes can occur, what have we done? And remember, our understanding of the causes of earthquakes has everything to do with plate tectonics. And we didn't even know about plate tectonics until about 1965. And by 1965, most of our infrastructure was already built. So we didn't know what we were getting into when we built most of the stuff that we see around us. But now we do know, and we can start making some changes. So what can we do to prepare? And like all good kind of steps of what to do in any situation, there's 3 things. Make a plan, build a kit, be informed. And of course, each one of those, it can be broken down into lots and lots of sections. These are just little visuals from various emergency preparedness agencies. This one I like because it breaks it down into, it's really, if you look at all the things that need to go into making a plan and building a kit, it's really extensive. So if you break it down and you just do one activity a month, so make a communication plan, check that off the list, create an action plan. There are lots of different websites that tell you what to do to accomplish all of these. Store water, that's a really important one. Get food. So you can kind of break it down over time. And the good news about doing this type of activity is if you're prepared for earthquakes, you're pretty much prepared for anything: wildfire, volcanic eruptions, COVID, or other pandemics. This is, if you have all of this in place, you're going to be good to go for a little while. And I think, you know, this really means a lot now more to people. When I would give versions of this talk pre-COVID, it kind of just is not something relatable. And now we can all relate to not being able to get the things we need when we need them. So that's just what this is all about. Here's Oregon Office of Emergency Management has full links to hazards in Oregon, earthquakes, volcanoes, how to put together kits for all of these. The good news with preparing for volcanic eruptions is that the Cascades Volcano Observatory, it's a USGS office located in Vancouver, Washington. They monitor all the Cascade volcanoes, and if they're in, volcanoes are great. They give us warning before they erupt. If there are any signs of volcanic activity, you will hear about it, and they will have information on what to do. Earthquakes, because the large Cascadia earthquakes can cause so much damage throughout the state, that takes a little bit more work to prepare for. So be ready to know what to do during an earthquake. Practice. You can talk about drop, cover, and hold. See, everything has 3 things you do. During an earthquake, you drop, cover, and hold. You could talk about that for hours, but unless you actually practice doing it in a limited amount of time, you're in a room, find a safe place, drop, cover, and hold on to something strong and protective in that room, like a large table. So if you don't know what this is, look it up. The Great Oregon Shakeout is a really good website. Once a year, they do a practice of drop, cover, and hold across the state. You can practice this with everyone else in the state, and actually everyone else in the world kind of does this more or less at the same time. It's in October, but don't wait until October. Check out this website, see what drop, cover, and hold means, and practice it. Practice is the key to all of this stuff. Make a disaster plan that includes how you will communicate with others in an emergency. And I just put this in here. Employers have a role to play in this because these things need to be done on an individual level and also on an employer level. Because if you want your business to be up and running after an earthquake, you need to make sure that your employees are protected and can come to work. Build a kit. So grocery stores, I used to use this slide. Grocery stores are well stocked with tasty, non-perishable food. And you can see this very enjoyable shopping experience. And we all know now, because of COVID, that grocery stores aren't always well stocked. But they're pretty well stocked now, and you can build up your emergency kit now. And unlike COVID, you know, you might have really wished in the beginnings of COVID that you had been stocked up on toilet paper or chicken or whatever the next thing was going to be. You never know what the next shortage is going to be. But after an earthquake, that's what grocery stores are going to look like. Not only will the shelves be empty because nothing is coming in, there is no transportation to provide food, but everything in the store is destroyed. So this is really, you know, stocking up on some emergency supply food and non-perishable items in the sense of an earthquake is very different than in the sense of a pandemic, in that really that stuff isn't going to be available at all. And then, you know, there are lots of things. I like these guys, the Preparedness Ninjas. This is from British Columbia, these little bears that go around preparing their homes. Strap your water heater, bolt heavy objects to the wall to keep them from falling. So there's lots of information online for how to make your home safe for earthquakes. Know where emergency shutoff valves are for gas lines and keep those tools nearby. This is an image from the 1995 earthquake in Japan that caused huge fires. And that's actually the most damage caused by earthquakes is fires because gas lines rupture. Japan now has a system where these gas lines automatically shut down and they don't have fires caused by earthquakes. We're not there yet. So know how to shut off your gas lines. I'm kind of going from easiest to hardest of things to do to prepare your house. But evaluate buildings for safety and make seismic retrofits. And so this gets back to that app that you can use to check out the buildings in Portland. Homes that were built before 1974 are at the most risk, and that's how they inventoried those homes in those buildings in Portland. It's just based on the year they were built. So if your building that you live or work in was built prior to 1974, you might want to check out seismic retrofitting. homes and buildings built after 1993 are at the least risk, and the ones in between are kind of at a moderate risk. So have someone come and check out your home. This home, let's see, this house has been seismically retrofitted. This is in California. This house has not. It's still standing, but it is not safe to enter that house because it has slid off of its foundation. So even though it's not just a pile of rubble, it's still not a safe. You can't go and occupy that home after an earthquake. Participate, this is a huge one. Participate in community informational events and planning exercises. This tomorrow, Corvallis is doing a community-wide evacuation exercise. This is prompted by fire. So if the community needs to evacuate because of wildfire, here's a practice session to do it. But this applies to volcanic eruptions, earthquakes, all of what we've been talking about. So, and practice, it's just like drop, cover, hold. Practice is the key. If you practice this as a community, you know what to do when it really happens. So anytime you see, especially fire really prompts this. So if you see any wildfire community informational events, go to them. Because if you're prepared for wildfire, you're going to be prepared for all of these other things as well. If you want your community to do something like what Corvallis is doing tomorrow, be a squeaky wheel. Ask your community to do that. Learn about geologic hazards where you live and play. This is just, I have links to all of these at the end of the talk, but the Oregon Department of Geology and Mineral Industries has these great interactive maps that you can zoom into your exact house in your neighborhood and look at what geologic hazards exist there, earthquakes, landslides, floods. So they're kind of nerdy to play around with. This hazards one has all of them in one. You can see there's a landslide map, a tsunami map, a Mount Hood hazard map. This map combines those all into one. And so they're a little nerdy to play around with, but they really give you great information. Places that you go, are they susceptible to these hazards? And finally, invest in infrastructure, preparedness, and planning. We need to, this is going to be costly to change situations like this, but we need to invest in this type of thing. And the state is already doing that. When I gave this talk pre-COVID, we did not have this system called Shake Alert. We have it now. It's an early warning or early earthquake warning system. And what it does, because of the way earthquake waves travel, the first wave that comes by, the fastest wave, doesn't cause damage. And the second wave that travels slower does cause damage. And so you can use the difference in time between the first and the second earthquake waves to send warning out to people. It only gives several seconds to minutes of advance notice. It depends on how far away you are from the center of the earthquake. And that doesn't sound like a lot, seconds to minutes, but that's enough time for people to take cover, to stop delicate medical procedures. If you're having surgery when this happens, you want the doctor to put everything down. And this is ample time for that to happen. You can stop traffic on freeways, clear ramps and bridges. You can shut down any automated systems. In Japan, trains automatically come to a stop. Gas lines shut off. Japan has taken this much farther than we have, but that's our goal, is to get to the level of Japan. So check out Shake Alert. Get the app on your phone so that you'll get a notice when earthquakes occur. All right, I'm almost done, just a few more slides. Investing in infrastructure and preparedness planning. This is a hospital in Japan, and this picture was taken after the 2011 magnitude 9 earthquake. And there is not a pane of glass that is broken on this hospital. The thing was fully functional right after the earthquake and was taking people in. Oh, sorry, I should have got this up earlier. This hospital, the original hospital, was located in a tsunami zone, and so it was closed and rebuilt. This is the new one. We have scenarios like that here in Oregon. We have hospitals that are located in tsunami zones, and they are not being rebuilt in other areas. We have schools that are located in tsunami zones. It was rebuilt, and it was rebuilt with these structures holding up the entire building called base isolation. They're essentially springs that are separating the building from the ground. And so when shaking occurs, these things absorb that shaking. And that's why there was zero damage to this hospital. Here's another image of what that looks like. The building is actually kind of floating on these highly engineered springs. So this hospital was up and running immediately after the earthquake. And remember, if we could do this here, we could get rid of this 18 months or however long it's going to take to get critical facilities back up and running. It's expensive, but the payoff is more than worth it. Okay, so that kind of went from easy things to do to very hard, expensive things to do. So conclusions, we know there will be future earthquakes and volcanic activity in Central Oregon. This isn't if it will happen, it definitely will happen. It's just how long into the future will it happen? We're not fully prepared for these events, especially large Cascadia earthquakes, but we can prepare for these events. Oftentimes when I give these talks, people are just like, there's no way, we're all gonna die. Like, why do anything? That is definitely not the case. We have the technology to prepare for earthquakes. We can have a magnitude 8, a magnitude 9 earthquake and not have very much damage at all. It happens in Japan. It can definitely happen here, but it needs an investment in infrastructure, economy, and it needs a culture that responds to, these kinds of preparation steps. So that's the end. I'm gonna just kind of leave this up. It has lots of good sources of information. And if there's any questions, I'll take questions. And I'm sorry I did go over.
Wow, that's fascinating. Yeah, awesome. Yeah. Do you have any questions? People at home, do we have any questions for Danielle?
Did I overwhelm everyone?
Yeah, so you mentioned in Iceland, one of the main things that they had to deal with was snow and flooding.
Yeah.
And that's going to potentially occur in Central Oregon too, because Cascades are snow-capped most of the year.
Yeah.
So then you were also talking about the ash, and you showed us like how your car might even start. How do you go about even cleaning up that kind of thing? Like water, snow will melt, flooding will occur, things, but then it goes away.
Yeah.
Ash does not. What do you do?
Absolutely, and that's one of the biggest problems with ash is cleanup. You can use, so here in Central Oregon, we have less snow removal equipment than we used to in the past.
Oh, yeah.
Seems like our budgets for snow removal have really gone down, but we do have some snow removal equipment. So you can use some of that. You can use plows to get ash off the road. It's obviously not going to get it all off. One of the biggest problems in that regard is where do you put it? You can pile up snow in unused, empty lots or things like that, and it will eventually melt. Ash, it's really hard to then find a storage place for all that ash that you've cleared from roads and roofs. And then in other places, like the Willamette Valley, where there's not much snow removal equipment at all, it's really difficult to then remove that ash. So that's just one of the biggest problems with ash you've identified is just getting rid of it. Not only do you have to move it off of your roof or the road or wherever, but then you have to put it somewhere, and that can be really hard to deal with. And then it just keeps remobilizing. Even though you've moved it off your roof isn't in danger. For decades, the wind can pick up that ash and blow it around. And in Central Oregon, it's dusty. Everyone knows it's dusty. If you don't like dust on your shelves, you kind of have to like be on that every day, right? Most of that dust is volcanic ash from volcanoes that erupted thousands of years ago, and it's still kind of rolling around in the system. And if we had an eruption, today, that would create a whole bunch of more ash. So it's a nuisance on a kind of annoying but harmless level, and it's a nuisance on a really health risk level. Like you don't want to breathe that ash in because it can cause damage to your lungs. And all of the disruption of electric lines or the electric system in your cars or even cell phone towers. It can oftentimes cause disruptions there, so in communications. So it really is kind of the most widespread and low level. It's not going to cause a lot of death, but just a lot of kind of economic and low level ongoing annoyance issues.
Yeah, it's almost reminiscent of the Dust Bowl.
Yeah.
Because then it would cover ground.
Yep.
Food and.
Yeah, absolutely. So growing crop, we don't have, most of our food doesn't come locally. Earthquakes really disrupt, getting our food supply in from other places. But ash does, whatever agriculture does happen here, that's going to have a big impact on agriculture for sure. And, we looked at livestock, it impacts livestock.
Yeah.
Iceland is a little different than the US in that they bring all their livestock in for the winter. So they mostly have horses, sheep, and some cattle. We saw cattle there. And they have big barns and they bring all those animals in the winter. We don't have those. Our animals are out year round. Some people have barns, but that isn't like how agriculture, livestock is generally raised in Central Oregon. So if there was widespread ash deposits, just getting all of those cows ground up and put somewhere safe would be hard to do. So yeah, lots of things to think about in terms of ash. Also water supplies, it can contaminate water supplies, drinking water supplies. So that it really is, I just barely touched on ash, but that really is one of the kind of longer term problems that we could deal with.
Absolutely. I thought it was great the way you put into perspective pre-COVID versus post.
It really has changed, yeah.
So, the references that you use, it's feasible, I'm not quite 30, I wasn't around for many of the things you talked about, but now I have big thing, and there's just so much more of a actual understanding, and I think that will hopefully, propel people towards more action preemptively because we've all witnessed it.
Yeah, and it's daunting. I have worked on putting together, a kind of the full extent of that, make a plan, build a kit, that whole thing. It's a lot, and I would say that mine, like all aspects of mine, aren't totally done yet.
Yeah.
But that idea of just doing one of those things a month really is helpful, because then you can just sort of slowly check it off. There's another kind of socioeconomic and cultural issue there that we need to deal with, which is that some people have a hard time just getting dinner tonight.
Yeah.
Putting together emergency supplies for a month is not something that they can do. And so there are, as a society, again, kind of in that last slide, we need to address it as a society, and that's part of what needs to be addressed.
Definitely. In one aspect, we're lucky in Central Oregon that we've had such growth and development over the last few years because so many more of these buildings will actually be up to code, at least in the residential areas.
Yeah.
So, if we don't have a city hall, many people will probably be saved because their buildings were completed last year.
And one thing I didn't touch on, there has been some retrofitting of schools across the state, not all of them, but some of them. So we are making progress. That shake alert, that's huge. Like for decades, lawmakers in Oregon were trying to get funding for shake alert, and now we have it. So things are changing. Not all schools have been retrofitted, but many of them have. So, it's slow, but we have time. This earthquake could happen tomorrow. It could happen in, 100 years. So let's just take the approach that's going to happen in 100 years and make these steps that we need to make to prepare for it.
What does it take to get a community to have regular drills? Like, I grew up in San Francisco where it was like earthquakes all the time. It was a no-brainer in school. Every month we had a drill.
Yeah.
And we were just prepared. And what does it take? Like, they have the tsunami towers and on the coast.
Yeah.
People,
I think, that's a really good question. And I think what it takes is something bad happens. And then then people are, oh yeah, I really do have to pay attention to this. And I think we are already seeing that happen in Oregon because of fire. I think that for many, many years, community planners and especially wildfire management agencies, the agencies that are involved in actually fighting the fires, have really tried to get community to take part in these events. And it has been very difficult to do. And then we had a couple years of really big fires impacting very densely populated areas. And now everyone is thinking about fire. And so much so that the city of Corvallis is doing a full community-wide preparation event. And so I think that we're getting there now because of wildfire. People are really seeing, oh, we all live in an area that could be impacted by wildfire. Before it was sort of, oh, you just have to be in the woods and on the east side of the mountains. And we saw 2 years ago, they can occur on the west side of the mountains and they can affect huge, areas. So I think people's perceptions of wildfire are changing. And because of that, they're more likely to be involved in these events. And once you're ready for one of these sort of hazards, you're kind of ready for all of them. So that I think, I mean, that's one benefit. It's one sort of silver lining of these big mega wildfires that we're dealing with now. You know, obviously there's a lot of negative aspects of that, but one is people are kind of paying attention. It definitely got people's attention. And then that might change how prepared we are for these other
And
events.
also funding, you know?
Yeah.
Like funding from the government, so like resources.
Absolutely. And it's the same thing there. What triggers funding, unfortunately, is something bad happening. But then the funding does open up. So
Marilyn from online is curious, when Cascadia hits, will it cause our volcanoes to erupt?
oh, you know, I meant to touch on that.
Reaction?
Yeah, so it's a great question. I meant to touch on it when I had that slide showing subduction, because everyone asks that question. You know, a few decades ago, the answer would be no. There's no relation between big subduction zone earthquakes and volcanic activity. But the more we study it and the more people kind of look at volcanoes that have erupted after large subduction zone earthquakes, there does seem to be a little bit of a link. And it's not the kind of link that if we feel the shaking of the Cascadia earthquake, and we would know that that's what we're feeling, it would last for 5 minutes. We would feel it here in Central Oregon. It wouldn't be as strong as in the valley and on the coast, but we would definitely know it's happening. So if we feel that shaking, then we don't just have to run out to the window and look at all the volcanoes and see if they're erupting. It's not that close of a link, but it does kind of look like if there's a volcanic system that is kind of primed, it has magma in it, and it might erupt in the next 50 years, maybe it erupts in 20 years instead, or maybe it erupts in 2 years, because it is somewhat impacted by that shaking. So there's no direct link. You have the earthquake and then you get all these volcanoes erupting, but there is, you know, they are both caused by subduction. And so there may be some small, you know, links there. But for you and I, really, the basic message is there, we just need to be prepared for earthquakes and volcanic activity all of the time. And, you know, we hope they don't occur at the same time, just like we hope that volcanic activity doesn't trigger massive wildfires so that we have two things going on at once, but we need to be ready for that if it happens.
And one of the best ways is by experts such as yourself educating the community. So thank you, Dr. Daniele McKay, for being here today. This is great.
Thank you. Thanks so much.
Well, thanks everyone who is at home for joining us today. We hope that we'll see you again soon in person, and don't forget you'll get a recorded link to this presentation following today's program. So thanks so much, everyone. We hope to see you next time. Check out DeschutesLibrary.org for all of our other great programs. Take care.